welcome again to physics class of alternating current part 3. In the previous videos we have discussed about that alternating EMF and current and this average or mean value of AC current, root mean square value of AC current, AC circuit with resistor, AC circuit with inductor and AC circuit with capacitors. Okay, and in today's class we will try to discuss about the AC circuit with the series connection of LC and R, resonance of LCR circuit, Q factor, and then we will have to discuss about the power in LCR AC circuit. So let's go through that of AC circuit with LC and R in series. So AC circuit with LCR in series combinations. Series combination means the resistor, capacitor and inductor, all these three components are connected in series. And so we know that when these three are connected in series, the same amount of current will flow through these different components along L, that means through L, inductor I mean, through C and through R. All the current flowing through these different components, okay, will have the same amount of current. Now these three components L, C and R, they are connected in series with a source of EMF of whose instantaneous EMF is given by E is equal to E naught sine of omega t. Now the applied EMF appeared as a voltage drop, okay, that depends upon the amount of current flowing here. So let that instantaneous potential drop across these different components be denoted by VL. Okay, the potential drop that is across L, that is denoted by VL. Potential drop across this capacitor is denoted by VC. Potential drop across the resistor is denoted by VR. Now we know that in a circuit containing resistor, current and voltage are in phase. But in the case of inductor, okay, current lags behind that of voltage by a phase difference of pi by 2. And in capacitor, current leads the voltage by a phase of pi by 2. And the phasor diagram is shown here. Collectively I am drawing. Okay, for this one, red will give you the phasor for the current flowing through these different components in series. That means I is the current flowing through L, through C and through R being in series connection. So same amount of current will flow through them. So let that I be denoted by here with the red, okay, line, and this VR is the potential, okay, across R, potential drop across R, that is denoted by VR. So as in the AC circuit containing what resistor, current and EMF or voltage, they are in phase, so they have to be drawn. That means current and potential drop or voltage should be drawn along the same line. But in the case of inductor, we know that current lags behind its voltage by a phase of pi by 2. So this will represent the voltage across L. That means voltage across this inductor is denoted by VL, and it leads then the current by a phase of what? Pi by 2. And again in the case of capacitor, what happened? The voltage across the capacitor that is lagging behind, then the current flowing through it by a phase of pi by 2, or rather you can say in the case of capacitor, current leads its voltage by a phase of 90 degree or pi by 2. So what happened if we are going to do the series circuit of these three components? Then instead of having this VL and VC opposite to each other, what happened? Let's take it that VC along this positive side. Now this VL and VC, we are considering here this VL and VC, VL greater than VC. Now this VL and VC depends upon the angular velocity of the AC circuit or AC source, or rather we also call it angular frequency also. So what happen, it depends upon the angular frequency omega. So in some case what happen, omega L is greater than omega C, and in some situations of the value of this angular velocity omega, your Vc may be greater than VL. So we are taking at a situations where VL is greater than Vc. Now if VL is greater than Vc, and if we try to make it this Vc onto this side, then by putting a minus, this is a vector quantity, okay, vector quantity Vc, as it is a phasor. So what happen, it will be a rotating vector, right? So your Vc representing here, this is a vector quantity. So if you want to make it in the opposite direction, then you have to put one minus, and of equal length here, from here to here of equal length, you take it in the opposite direction. Okay, this is the origin, this point is the origin, you take it as O here. So if you make it opposite, then it will be minus Vc. So now if we try to have these two vectors VL and Vc in the same direction, okay, Vc means minus Vc I should say. So as they are in the same direction, we know that the vectors can be added, okay. Then what happen, as they are along the same direction, so what happen, the difference of these two, that means VL minus Vc, rather VL plus or minus Vc, that will be equal to VL minus Vc. It will be coming somewhere around here. So if you remove, if you subtract from VL, if you subtract this much portion, then this much remaining portion is shown with the violet, okay, that will be nothing but this length will be equal to what, VL minus Vc. That VL minus Vc, it will be coming from somewhere here. And if we can have the phasor of that VL minus Vc somewhere here with that of this VR, then it will be coming in like this. Let's see. So these are the equations that to be coming. So see that VL minus Vc, if you draw it here, then it will be like this. So this much vector is what, VL minus Vc, and the magnitude of this will be equal to this violet here. What is this violet? Violet is nothing but violet line, I mean the length of this violet color length with the arrowhead will be equal to what? It will represent VL minus Vc. And if you make it that these three vectors VL, Vc, so VL minus Vc will be indicated by this, and VR will be indicated with this blue line, okay. No doubt I will be denoted by what, the red arrow line, okay. So what happened, we can have two vectors, you can say VR along x-axis and another vector along y-axis is what, VL minus Vc. So if you try to complete the parallelogram, in our case it is rectangle, okay, then if you try to complete a rectangle, then the diagonal will give you the resultant of VR and VL minus Vc, right? So the diagonal will represent the resultant vector of VL minus Vc and VR. So we will get this as the EMF, okay. So this EMF is nothing but the instantaneous EMF of this LCR in series, okay. Now let's try to see what are the equations that depicting all these things. Now your instantaneous EMF is equal to what? From this diagram you can find it out very easily, that by taking the help of that parallelogram law of vector addition that you have learned in class 11. So what happened, the resultant of this diagonal, okay, the magnitude of this diagonal will be given by what, root over of VR square plus of VL minus Vc whole square, okay, plus cosine of this V twice of this VR, VL minus Vc magnitude I mean, times of cosine of phi or theta, where theta is the angle between these two vectors, but that one, as it is 90 degree, so no need of putting that one. So if you want to just remind you again, then what happened, we know that if there is a parallelogram like this, okay, one vector along this, another vector along this, let's take it that this is a P vector and this is Q vector like this, and the angle between them, if it is theta, then if you try to complete the parallelogram like this, then the resultant of these two vectors will be given by what? The diagonal drawing from the same point. Then your diagonal will be equal to r square is equal to what? P square plus q square plus twice of pq cosine of theta. You must be remembering that in your class 11. Okay, so if you want to find out the magnitude of these r, then you need to take the square root of this quantity, right? But in our case here, what happened? The angle theta, this angle theta is what? 90 degree here. So if you put that cosine of 90 degree, then this part will go to 0. So no need of putting this one. And if you want to find out the magnitude r, then you need to take square root of this, right? So that is what I'm having here. P, you can take it P as VR, and Q, you can take it as VL minus VC. So what happened? Your resultant, the diagonal, which represents by diagonal, will be given by what? E. So your E will be equal to what? Your E will be equal to BR square plus BL minus BC whole square. Got it? So root over is there. So what happened if you want to find out the current again? Then we know that from Ohm's law, E by R is equal to what? Your instantaneous current. From where it is coming actually? Now what happened? This V actually, from where it is coming, let me tell you. Okay, now we know that E is equal to what? Root over of what? B square means I square R square. This is nothing but this is your BR square. So plus BL means the same current I, then this XL. Okay, XL is the inductive reactance. Current into its opposition inductive reactance will give you what? Your VL. Got it? Minus BC means what? That current I times XC whole square, like this. So if you take it this I square root over of what? I square, you take it common, then it will be what? Within the bracket it will be R square plus of what? XL minus XC whole square, like this, right? So if you take this I square, okay, square root of this, then it will be coming I. So it will be equal to I times of what? Root over of R square plus XL minus XC whole square, like this. So we call it this as what? Impedance. Impedance, and it is denoted by Z. What is this Z? Z is equal to nothing but this will be equal to what? Root over of what? R square plus of XL minus XC whole square. We call it this as impedance, and impedance means it is nothing but it is the effective resistance of the LCR series circuit. That means the effective opposition offered by these three components to the flow of AC current, we call it that as impedance, and it is denoted by Z. So your Z is equal to what? R square plus XL minus XC whole square, and root over of it will be equal to what? Your impedance. Got it? Yes. Now after then what happen? If we want to find out the instantaneous current, then it will be what? EMF by its impedance. Okay, EMF, that means voltage divided by resistance, will be equal to what? Voltage divided by its resistance will be equal to current. So in our case, voltage means our resultant EMF, rather resultant instantaneous EMF divided by impedance will give you what? Your instantaneous current. So your Z is equal to what? That is your impedance written here. So it can be also expressed in terms of angular velocity also. This is angular frequency or angular velocity, you can call it. Okay, so omega is equal to what? Twice pi f, and xl will be equal to omega l, where xc, the capacitive reactance, it will be equal to 1 by omega c. So whole square of it will give you this impedance. So impedance can be either represented with r xl xc or with r omega l omega c, like that. So these two equations can be used for finding out what your impedance. Got it? This is in terms of the resistance and reactance, and this is in terms of the resistance, angular frequency, inductance, capacitance. Okay, this will be the relation for that of the impedance relation, impedance. Okay, the relation for impedance can be used for these two. Now what is this tangent phi? Now why I am taking this tangent phi? Because it will be used at the time of that power and all. Okay, so let's try to have it. So from this triangle, okay, from this from this diagram, phasor diagram of the LCR circuit, now you see that if you try to find out tangent of phi from this right triangle, okay, from this right triangle, can you see there is a one right triangle here? This right triangle, the angle that is formed by the instantaneous EMF with that of the current, okay, that angle we call it as phi. So what happen if this phi, if you want to take it tangent of phi, that means perpendicular by base, we call it that as tan phi, right? Tangent of this phi, where phi is the angle between what your instantaneous EMF or voltage across what R, you can say. Okay, voltage across R, this is what phi. So if you want to find out tangent of phi, then you need to take it this perpendicular divided by base. Perpendicular is what? VL minus VC. Got it? And base is what? VR. So if you want to find out that tangent of phi, then what happen? You will get it as what? Tangent of phi, let me write here, tangent of phi will be equal to what? VL minus VC divided by VR, right? So instead of this VL minus VC, you can write as what? In terms of its reactance and the resistor. So if you do that, then VL will be equal to I times XL. Okay, VR will be equal to I times R, right? And in this case, VL will be I times XL minus VC means what? It will be I times XC, like this, right? So what happen if you take that common of this current I, then what happen? Then this I can be cancelled with this. So what you remain is that tangent of phi will be equal to this much only, XL minus XC divided by R, right? So in terms of the reactance and resistance, you can express tan phi like this, or in terms of what angular velocity, inductance, capacitance and resistor, you can express like this. So tangent of phi will be equal to what? XL minus XC by R, or tangent of phi can be also expressed as what? Tangent of phi equal to omega L minus omega C divided by 1 by omega C, omega L minus 1 by omega C divided by R. Now that is what just I have told you, that tangent phi will be equal to what? XL minus XC divided by R, or it can be also expressed as omega L minus 1 by omega C divided by R. Now let's see some special cases. Okay, what will happen when XL is greater than XC, or XL is equal to XC, or XL is less than XC. So depending upon these three, you will have three cases. For the first one, let's take it that XL is greater than XC. That means your inductive reactance is greater than that of capacitive reactance. That is what? XL greater than XC, or you can call it this omega L is greater than 1 by omega C. then what happen? If this XL is greater than XC, then what happen? This will become positive. So the whole ratio will become positive. That means tangent of phi will be positive. If tangent of phi is positive, that means phi is positive. Phi positive means what? Phi will be acute. If it is acute, then what happen? The current, okay, the current will lag behind the instantaneous EMF. Now what was the diagram that we have drawn in the phasor diagram? It was like this: current along here and VL minus VC like this, VR here, and your E, instantaneous EMF, was here as a resultant in this direction like this, and this phi was like this, right? So if this phi is positive, that means if it is acute, that means what? Your current lags behind the EMF. Current is here, EMF is here. So that means current is lagging behind than that of the instantaneous EMF by a phase angle of what? Phi, right? By a phase angle of phi. If it is like this, then what happen? If the current lags behind the instantaneous EMF, it means that the circuit is what? Inductive dominance or inductance dominance, okay, circuit. Got it? And moreover, the nature of the circuit will be what? Just like inductive. Got it? So we call it this type of circuit as what? Inductance dominated circuit. Got it? Yes. In the next case, case number 2, when these two XL is less than XC, that means your inductive reactance is less than that of capacitive reactance, or rather you can call it this capacitive reactance is greater than that of inductive reactance. In that case, what happen? Omega L is less than 1 by omega C. So if this one is small and this one is large, then what happen? The difference will become negative. The difference of these two, I mean, it will become negative. If phi is negative, that means if tangent of phi is negative, that means phi is what? Negative. If tangent of phi is negative, that means what? This angle is also negative. In that case, what happen? Current leads the EMF by a phase of an angle phi, and LCR circuit is said to be capacitance dominated circuit. And the nature of the circuit will be what? Capacitive in nature. In this case, what happen? Your current what? Leads the EMF by an angle of what? Phi. Got it? But in the next case, let's see, when these two are equal, that means when the inductive reactance is equal to capacitive reactance, or omega L is equal to 1 by omega C, then this ratio, okay, will become 0. Why? Because the numerator is 0. Numerator 0 divided by a non-zero quantity, it will be 0. So your tangent of phi will be equal to 0. Phi 0, tangent of phi 0 means what? Phi is 0. So in that case, what happened? The current and the EMF are in phase. The current and EMF are in phase means what? The impedance does not depend on the frequency of the applied EMF. In this case, what happened? LCR circuit behaves just like a pure resistive circuit. And in this case, what happened? Your impedance will be very, very small, and it will be equal to that of R. Your Z will be equal to capital R, and the current will be maximum in this case. Got it? So let's see about the resonance in LCR circuit. Okay, when XL is equal to XC, that the last case. Okay, when XL is equal to XC, or rather omega L is equal to 1 by omega C, that happens when tangent of phi is equal to 0 or phi is 0. That means what? When your instantaneous EMF and what current are in phase, then what happen? That happens only when this XL is equal to XC, and this condition we call it as resonance condition. So if the impedance offered by the circuit is minimum, in that case what happens? Z will be equal to R. Z minimum will be equal to R. Z minimum is nothing but the impedance. Okay, the impedance is minimum, then it will be equal to R. Why? Because these two are equal, and if these two are equal, then the difference of these two, this term, second term, will be equal to 0, and this will be R square root over. So it will be equal to what? R only. So your Z will be equal to R, and it is the minimum value of Z. When impedance is minimum, naturally your current will be maximum. So your maximum current will be equal to simply what? Your instantaneous EMF divided by the resistance. Because Z is only R here now, okay? So your E by R will be what? Maximum. That is given here. The impedance offered by the circuit is minimum and the current is maximum. Okay, if the opposition is minimum, naturally the current flowing through it will be maximum. This condition is called resonant condition of LCR circuit, and the frequency is called resonant frequency. Now let's see. Now if you are having that curve between the current and the angular frequency, then what happen? The curve will be obtained like this. Okay, where whatever be the value of L and C, it is immaterial. We need to consider only about the value of the R. Okay, we are having three curves for different resistors, R1, R2, R3, and R1 is the least out of these three. R1 is less than R2, is again less than R3. So R1 is the least. Okay, we are trying to take or replace the resistor by the three resistors of whose resistances are R1, R2, R3. So when we draw that curve of different resistance in the LCR circuit, okay, keeping L and C constant, and if you are trying to draw the graph between the current and the angular frequency, then what happened? The curve will be obtained like this. When R, okay, resistor, if this resistance of the resistor is less, then the peak will be very high. Okay, if the resistance increases, then what happened? The peak decreases. Okay, if again resistance increases, the peak will again still decreases. Now what happened if we try to increase the angular frequency? Okay, then what happened? At both sides of this angular frequency, okay, the curve decreases. That shows that current decreases. Okay, whenever the angular frequency goes away from that of the resonating frequency or resonant frequency, what happened? The current decreases. But at the angular frequency equal to the resonating frequency or resonant frequency, at that time what happened? As the impedance is less, the current will be highest. Got it? So I naught max is coming here for this one for resistance R1, but for resistance R2, what happened? I naught max decreases correspondingly. Okay, here also I naught max decreases, I naught max decreases, like this. Got it? So this is this curve. Okay, we call it this as what? Resonance curve. Now at resonant angular frequency omega, what happened? Omega R, instead of this omega, we can write it as omega R, where omega R is nothing but this is the resonant angular frequency. So at resonant angular frequency omega R, instead of omega you can write as omega R. So XL is equal to XE, right? We have to start it from there. So instead of XL we will write as omega L. So your omega will now be equal to omega R. It will be equal to 1 by omega RC, or omega R will be equal to 1 divided by root over of LC. Or if you try to express this twice pi f R, okay, instead of omega, if you replace it by twice by fr, then fr will be equal to 1 by of twice pi, okay, root over LC. Got it? So this is the what? Resonance frequency or resonant frequency, you can say. Now see this resonance curve and Q factor. Okay, let's see what is this resonant curve, that graph that is drawn between the current and the angular frequency. Okay, angular frequency, we call it that graph as what? Resonant graph or resonant curve. So if you take it that band wide Okay, from here you try to decrease by delta omega, and from this resonating angular frequency, if you increase by delta omega, then you will have a span of what? Twice delta omega, and that twice delta omega we call it as bandwidth. Okay, so if you try to decrease from this by delta omega, then this point will be equal to omega r minus what? Delta omega. So this point will represent what? This point will represent omega r minus delta omega. This point will represent omega r plus delta omega, so that this will be the width of one delta omega, another delta omega. It will be what? Twice delta omega. That is what it is written here. So if this is the bandwidth, then let's try to define it. The quality factor or Q factor, it is the ratio of what is this? Resonant angular frequency, right? Resonant angular frequency to the bandwidth. Okay, from this relation you can define what? The Q factor. Q factor is a ratio of what? Resonant angular frequency to the bandwidth. Okay, as this bandwidth is also having the same what? As the unit of frequency, this is also frequency, so this Q factor doesn't have any unit. Okay, it can also be defined as a ratio of, instead of defining in terms of angular frequency, you can define it in terms of the voltage drop. Okay, so you can also define this Q factor as the ratio of voltage drop across either L or C to the potential drop across the resistor. Okay, so that means it can be also defined as Q as what? VL by VR or VC by VR, where VL is the voltage drop across L, VC is the voltage drop across C, and VR is the voltage drop across R. So you can define it in terms of voltage. Okay, ratio of the voltage across L to R, voltage drop. Okay, ratio of voltage drop across C to R. Then what happened? You can write it Q factor as omega RL by R, or in terms of capacitance, if you want to write it, then it will be equal to 1 by omega R CR. So both this value will have the same, okay, value, this Q, even though it is in terms of inductance, in terms of capacitance, this Q factor will have the same value. That is why we define it in terms of either the voltage drop across L to the voltage drop across R, or voltage drop across capacitor to that of the voltage drop across R. Okay, now let's see about power in AC circuit with LCR series. Now we know that E is equal to E naught sine omega t, and I is equal to I naught sine of omega t plus phi, where phi is the phase difference between EMF and I. Okay, and instantaneous power, we know that instantaneous power will be the product of instantaneous EMF and instantaneous current. We know that power is equal to V into I, no? VI. So instead of V, we are having instantaneous EMF I. E into I will give you. So what happens if you take it this E as in terms of that's sinusoidal function? E is equal to E naught sine of omega t, I is equal to I naught sine of omega t plus phi, then you will get like this. So if you try to express this sine of omega t plus phi, okay, then what happens? It will be sine of omega t plus cosine of phi plus sine of phi cosine of omega t, like that. That means it is just like the expansion of sine of a plus b. Okay, and if you multiply it with this sine with that of those expansion of sine of omega t plus phi, then you will get like this. Got it? Yes. Now if the instantaneous power is assumed to be constant, okay, if the instantaneous power is assumed to be constant for an infinitesimally small time dt, that means during this small time dt, if we take it that the instantaneous power is constant, then work done is given by dw will be equal to what? E naught. We know that power work done, let me write it. Okay, power is defined as what? Rate of doing work, like that, right? So if you want to express this small amount of work, then the product of these two will give you the power. What is this? P is nothing but your instantaneous power, Pi, let me call it. That Pi will be equal to this. So your dW will be equal to instantaneous power times your dt. Got it? And if you want to find out the total work done, why we are going to find out the average power? So in order to find out the average power, we need to take it what? The total work done divided by total time. So if we are going to find out the average power, then we need to define it in terms of a complete cycle. Average power during a complete cycle. So we want to find out the total work done, not a small work done, rather to find out the total work done, we need to integrate it. Okay, this such small dW, we need to integrate it. Got it? If you try to integrate it, then the integrating limit should be from 0 to capital T, where capital T is your time period. So we need to integrate this dW. Okay, if we integrate this dW, then we will get it what? Just like this, W will be equal to what? E naught I naught cosine of phi into T by 2. Got it? So what happened? This T by 2, as I told you in the previous chapters, while we are solving those textual questions, I told you that the average power will be equal to what? E naught I naught divided by 2. It will be coming here also. Okay, let's see. For a calculation of this, if you want it, then I will send with the pictures. Okay, if you don't want, if it is okay, then it is very good. But doing this, it is not so much difficult. Okay, here integration of sine square, we have already done this one. Got it? That will come as cosine of omega t, cosine of phi only it will come, because this is here as phi, so it will be cosine of phi. But for this one, this will vanish if you integrate it from 0 to t. Okay, this will vanish. That means the value of this will all be equal to 0 when you integrate it. Okay, that is why it only remains about this cosine of phi. Got it? Yes. Now let's see your average power. Okay, which is denoted by P average, will be equal to total work done divided by total time. So during the time of that of a one complete cycle of AC, the time will be what? Time period. Okay, so total work done divided by total time, it will give you your average power. So if you divided this total work done by the total time period, TT will cancel and you will have only E naught I naught cosine of phi divided by 2, where cosine of phi, this will be equal to R by Z. From that phasor diagram, okay, from that phasor diagram, let me redraw it again. This is VR, right? And this is VL. This much is what? BC, right? And if you take it that VL minus VC, then it will come only this much, right? And if you try to complete this parallelogram, rather in our case it is rectangle, so if you try to complete the rectangle, then the resultant of this is coming here as E, like this. Got it? So this is what this length is, VL minus VC, right? And this angle we call it as phi, right? Your current I is somewhere here like this. No? So if instead of this showing in terms of the voltages, if we redraw it, then this BL, okay, instead of this, let's redraw it again. Okay, in terms of what? In terms of the resistance or the reactance, we can call it. So if we take it this VR as what? I into R, instead of this XL minus, instead of this VL minus VC, then we can take it as I times of what? XL minus XC, like this. So if you drop down this I from both sides, then this can represent what? The difference of the reactances, inductive reactance minus capacitive reactance. And on this side, this length can represent the resistance. This length will represent what? XL minus XC. So from this right triangle here, let me redraw it again here like this. Okay, this is your VL minus VC, this is your VR. So instead of that VL minus VC and VR, if we represent by the resistance R here, and this part by your XL minus XC, then this part will be also what? XL minus XC, right? So we call it this as what? Impedance triangle. If we redraw it like this, so this part will be equal to what? Actually your y-axis is here, x-axis is along this side, okay, like this. This angle is phi. This is equal to what? E. So we take it this as what? XL minus XE, and this part as what? R. Okay, so instead of that VL, that means in terms of potential drop, if we replace it by the resistance, then this triangle we call it as impedance triangle. So from this impedance triangle also we can define that of Z also. This E will be equal to I times Z, right? If we are going to replace it by the impedances or by the resistance offered, then what happened? This will represent what we call as this diagonal, I mean the length of this diagonal will represent the magnitude of the impedance. So your impedance that can be also obtained from this right triangle, that square root of what? R square plus what? XL minus XE whole square, like that. Got it? So from this impedance triangle also you can find it out. So your cosine of phi, we can express it in terms of what? In terms of that of your VR by E also. Instead of this VR by E, you can also replace by R by Z by cancelling those that IR divided by IZ. Okay, if you cancel it I like this, then you will get R by Z. Okay, so that is what I'm having here, R by Z. Got it? So here cosine of phi, we call it this cosine phi as power factor. But for your new syllabus, this power factor has been deleted, so I will not talk much about this cosine phi, or rather power factor. You just try to remember these formulas, okay? Instead of Z, you can replace it like this. So we call it this as power factor, okay? Now, instead of this E naught by E naught I time divided by 2, we can write it as E naught divided by root 2, I naught divided by root 2, because root 2 into root 2, it will become 2 again. So instead of this peak value of the EMF and current, we can replace it by its RMS value or virtual value, or we also call it that as effective value. We have already done this in the first video, right? So instead of E naught and I naught, we can replace it by EV and IV, where EV and IV are nothing but these are the virtual what value of the AC EMF and the current. Got it? That is the what formula for P average. That means average power in LCR circuit will be equal to what? RMS value of the EMF, RMS value of the current, and a factor cosine of phi is there. So this phi is nothing but the angle between what? EMF and the current. And this cosine of phi, we call it as power factor. So depending upon this factor, okay, whether your P average will be high or low depends upon this factor. Got it? If this is greater than 1, then this will be also very large. If this is very less than 1, then your power factor will be very low. If this cos phi is equal to 90 degree, then what happened? The average power will be equal to 0. So it depends upon this cosine phi. So we call it this as power factor, right? Now let's see it again in the different circuit, okay, containing with resistor, inductor, and capacitor alone. So from this formula, P average is equal to EV IV cosine of phi. In the case of resistor, we know that your current and EMF are in phase, so the angle phi, okay, will be equal to 0. So cosine of 0 is 1. So cosine of 0 will be equal to 1, means P average will be simply the product of the what? The EMF and the current. In our lower class, in class 10, you might have learned that power is equal to V into I. That is what we are having here. We never talk about the circuit containing inductor or capacitor in class 10. We were talking about that what? Resistors alone, is not it? So that is why we have the formula that power is equal to what? V into I alone. Okay, but if it is in the case of inductor or capacitor, what happen? Angle between them is what? 90 degree. Angle between them means about that EMF and the current. As in the case of inductor, what happen? Current lags behind the EMF by a phase of pi by 2. In that case, what happen? Angle between them is also 90 degree. In the case of capacitor, current leads the EMF by a phase of pi by 2. In that case also, angle between the current and the EMF is what? 90 degree. So in both the cases, what happen? The power factor will be equal to what? 0. Why? Because cosine of 90 degree is equal to 0. Now a point to be noted, okay, power or energy is not dissipated in the inductor and capacitor. Why? Because power is equal to 0. So in the case of what? Inductor and capacitor, no power is consumed. Okay, so what happened in positive half cycle, for example, power will be absorbed, okay, in the positive half. For example, in the next negative half, okay, in the second half, I mean, that power will be again given out to the source again. So what happened in total? What happened? No power is consumed. Whatever the power that is transferred to the component, either L or C, that much amount will be again sent out, okay, discharged to the source from these components again. So what happened in total? The average power will be equal to 0, and hence they find a lot of practical application, okay, in our day-to-day life and in a device using what? This is possible in the case of what? AC current. Okay, in an AC circuit containing what? L and C, what happened? There is no consumption of power. Got it? With this note, let's come to the end of our today's topic. Thank you very much for viewing my video.